Hello, welcome to Lenze training. This tutorial shows the basic structure of the TA project template provided by PLC Designer. The architecture of all TA projects is the same, and we will explore the TA sync and correction as a sample of TA user. The project consists of several objects in a project tree structure. Before we get into the application, look at the interfaces and their corresponding objects. Let us start with the EtherCAT master, which we are use as system bus master for the TA sync and correction. The encoder axis represents the optional second load encoder interface. The digital and analog IOs refer to the control signals via terminal connections. The onboard EtherCAT object is used as system bus slave for the TA. And the field bus refers to the field bus module with the connection to the higher level control. The safety interface is only relevant in case of extended safety functionality together with the i950 ES. Next we will look over the main objects of the application. The basic structure corresponds to the motion layer model. The first layer is the technology application itself under the folder A10 program call. This program contains the peripheral connections such as fieldbus and onboard EtherCAT connection and connection of the digital and analog inputs and outputs. The second layer is the control module. It is under the folder A70 control module sources. The program in the first function block contains the TA-specific motion functionality, implements an axis interface, and simulates the control and status signals. Another function block contains the access to basic drive functions, which are uniformly included in each TA. The third layer, the technology module, provides core functionality of the technology, and it is a part of a library, which is loaded by the library manager. The last layer, the basic motion functions, is directly assigned to the device's motion axis and represents the interface to the motion functions of the axis. The main program is called and calls high, and it is in the folder A90 resources. The call hierarchy of the program is structured in such a way that this calls high program calls the first layer, the technology application. This technology application calls the second layer, the control module, which itself calls the third layer, in which the basic motion functionalities are used. The main program is called in the main task with an interval time of 1 millisecond and executes the update of the system bus process image. That means it reads and writes the variables on the onboard EtherCAT. Furthermore, the program calls high calls the method call initialization once during the initialization of the i950 to prepare the communication on the system bus, and if necessary to start it in case of the EtherCAT master. Now let's us take a closer look at the first layer of the motion model, the i950 technology application. Double-click on it. The program is implemented in continuous function chart, short CFC. The main parts of program are the digital input interface, the touch probe interface, fieldbus/onboard EtherCAT input interface, the master value source selection, the fieldbus/onboard EtherCAT output interface, the master value output selection, the digital output interface, and the control modules. Please keep in mind that by changing the execution order, deleting function blocks, or modifying the logic, the TA parameters may lose their original function. Let us get into the details and start with digital input interface. In the digital input interface, certain functions such as hardware limits, reference switch, quick stop and reset error can be assigned to the digital inputs of the i950. These functions are programmed in the control module of the TA. As it can be seen, the output signal from the digital input interface is linked to the I/O input of the control module. The function config digital input of the Lenze library LDB2P is a multiplexer. Depending on the first input E selection digit, output can be set either to fixed true or fixed false or the value of second digital input. The data type of this second input SC digital inputs is the structure of LDB2P SC digital inputs, with 4 Boolean elements. Let us see how these elements are linked to the 4 digital inputs of the i950. In the project tree under the folder A55R lists you find the global variable list. In TAIO you see the declaration of the variable IODB2PSC digital inputs. The mapping of the related elements is in the digital I/O object. Here you find all the 4 elements of the global variable mapped to the physical digital inputs of i950. Let us go back to the multiplexer. The variable which are assigned to the first input is linked to a parameter. This parameter can be used to easily change the value of the variable via the parameter list or in the settings tab. You can find both tabs either in PLC Designer or in Easy Starter. Next we will move forward to second part of the technology application, that is touch probe interface. The function block MC touch probe is used to select and configure touch probe input functionalities. The TA sync and correction contains 2 touch probe blocks for master value correction and tool correction. The input E configuration touch probe is connected to a parameter of the TA. Let us go to the parameter list. Here in parameter 0x5020 subindex 11 you can see that in default setting the positive edge of digital input 1 triggers the first touch probe functionality. If necessary, the input can be reassigned. Furthermore, the i950 has the feature that a timestamp of the touch probe can be transferred to other connected i950s via the system bus. Parameter 0x5021 subindex 155 at the system bus input displays the transferred timestamp TP value. TP stands for touch probe. It is evaluated if external source is selected as touch probe source instead of a digital input. The inputs X window only, LR first position and LR last position can be used if a touch probe is only accepted within a certain window. Here in this parameterizable TA it is not used but may be added in the PLC project if necessary. The next part we will look at is the fieldbus/onboard EtherCAT input interface. The function block signal switch interface IN forwards the control signals from either the TA interface fieldbus or from the onboard EtherCAT. The source fieldbus, or onboard EtherCAT is set via the first input E source control word of the function block. The switchover at this input variable is performed by index 0x4001. The following function block switch axis ref extended combines the different measuring systems and extends the functionality and interfaces to the virtual master. The essential input is the selection of the master value source of the TA. Should the device follow the master value of another device, the system bus or the application feedback module of slot B must be selected. Alternatively, the device can generate its own set point by activating the internal virtual master, which generates its master value from profile data or with the help of the analog input. Let us go back to the program. The next part is the Fieldbus/onboard EtherCAT output interface. The function block signal switch interface out forwards the status signals received from the virtual master and the control module to the system bus onboard EtherCAT, or the Fieldbus depending on which control source is active by index 0x4001. Please note that the function blocks for Fieldbus/onboard EtherCAT interfaces in and out are not part of a library. Access to this program organization unit, POU for short, is only possible via the folder A90 Resources, which contains further local resources of the TA project template. The function blocks are open and freely editable and expandable. Now let us move forward to the next part, that is the master values output selection. The function block selection master values out is responsible for the data exchange when several i950 are connected to the onboard EtherCAT via the system bus functionality. The data that can be exchanged are own setpoint values, own actual values, the actual value of an encoder connected via the slot B, and values of the virtual master. The values can be configured via the parameter 0x5020 subindex 1, which is located on the overview page of the TA. It is important to know that only the system bus master decides which value should be forwarded to the other devices. This means that in each i950 on the system bus you can configure with the parameter master value output system bus which value is transmitted to the system bus master. Only the system bus master can then distribute the values to all slave devices. For an easy diagnosis, the values that are transferred are displayed in Communication tab, Onboard EtherCAT, System Bus Interface View. For example, bit 05 shows the timestamp TP, which is transmitted via the system bus to the other i950 devices. Finally, the variable U system bus out forwards the values in the structure LDB2P output data to the system bus via the procedure calls high. The double arrow indicates that the connector of the function block works as input and output. The next part is the digital output interface. The config digital output function block used is also a multiplexer. Depending on the first input E selection signal DO1, which is linked to a parameter, a status signal such as drive homed, brake release out, or signal from Fieldbus can be assigned to the only digital output of the i950. The last element but the most important part of the technology application is the call of control module, the second layer of the motion model. The control module, briefly called CM, contains the core functionality of the technology application, and is also programmed in continuous function chart. The CM has besides the control signals some other variables like parameters, persistent data, I/O, and the references of the master axis and motion axis as inputs. Double-click on the CM in the technology application or open it in the device folder A70 control module sources to see how it looks like. The CM is also a part of the project template, which you could modify if necessary. Similar to the technology application, it is important to ensure that the execution order is not changed in the control module. The main parts of the CM are the input signals, the control signals, the technology module, the signal flow, the axis interface, the limiter, the error handling, the monitoring signals, and the status signals. Again, we would like to take a closer look at the essential functionalities. Let us start with the input signals. The variable I/O of the data type CMIOSC sync and correction is connected to a CFC element selector, with which the individual components of the data structure can be accessed. To add further variables to the data type if required, you can find the definition as a separate element in the TA project template. The master value is included in the structure as well, but is hidden in the signal flow for better visibility. Next we look at the handling of the control signals, which contains two elements. First, the control word simulation that is used for the internal control function. This function can be activated via the Settings tab of the Easy Starter or PLC Designer to disconnect the field bus or system bus from the control module and enable simulation. The second box is again a CFC selector to access the individual elements of the control signal interface, such as control bits or setpoint values. Next, we look at the technology module, short TM, which provides the core functionality of the technology. For the TA sync and correction, the TM is used in the state version and is called sync and correction state. The control takes place via the previously described control signal interface but can also be done via IOs depending on the parameterization. The status signals provided by the TM are transferred via the CFC element composer to the control module output on the field bus and onboard EtherCAT. The part signal flow below the TM is used to visualize parameters in the Settings tab of the device. Some parameters are directly linked to variables of the technology module. Further required parameters will be prepared within the signal flow part in the control module. Let us move to the axis interface. The function block LTB2P axis interface is the interface to the motion axis ref of the technology application. On the one hand, the interface enables access to various axis functions such as brake control, speed and position controller or hardware limit switch. On the other hand, the interface provides various axis information such as motor current, DC linked voltage or motor temperature, which are assigned to the output of the control module. A further part of the control module is the limiter. The limiter is used for the i950 extended safety and is connected directly to the safety interface. The safety interface in the device tree contains a variable limiter control, which is mapped to the limiter in the control module. The variable serves to limit drive speed and to react to requirements of the safety interface. Error handling. First, we look at the set error function block. We have a functionality called Lenze Error Management, LEM for short, which handles all occurring errors. Errors of the technology application are transmitted directly to the LEM for the processing. The unused inputs on the set error function block can be used to trigger user-specific errors or warnings. Each trigger event will be output with a corresponding error ID. Depending on the defined severity of the error, activating this event can cause a drive reaction, for example quick stop. This logic can then be used to acknowledge a pending error or warning. This can be done via the control module interface I/O and control signals. In the error handling, there is another function block, called Read Actual Error Code. The name says it all. That means that it reads the current error code including the error severity from the LEM and outputs it to the status signals of the technology application. Next, we have the monitoring signals, which can be forwarded to a high-level control via fieldbus or onboard EtherCAT. The signal selection is realized again by a multiplexer, which is linked to a parameter. Let us have a quick look at the Settings tab. The function block source monitoring signals multiplies the monitoring signal selected by the first input with a factor, and converts it into a double word value without decimals. For example, the motor temperature is output to the status signals with the factor 10. Finally, we are back at the function block status signal sync and core action, which collects all states and saves them in a structure. The linked function block status word simulation is the counterpart of control word simulation when internal control is active. Before we finish this section of the control module, we briefly swap to another function block. The CM Basic Drive Functions contains access to drive functions that are provided independently of the technology application used. This control module contains the interfaces for activating additional basic drive functions such as manual operation open loop, or brake test. Next, let us look to the last point in the structure of the TA project template, the global variables. Under folder A55R lists you will find the global variable lists. TADCL contains the declaration of all function blocks in the application, as example the control module. The list TAIO contains variables that are connected to the periphery of the i950, the digital and analog in and outputs, the safety interface, and the system bus slave interface. TAPAR contains the declaration of parameter structure, for example TA parameters and user parameters. So, if you need your own parameters, please declare them here in the list. And finally, the TAPD contains the declaration of persistent data. The variables declared here are not only saving data during power failure but also download save. So, if you download the project, the persistent data remains unchanged. By now, we know the structure and meaning of the main functions in the TA project template.